Now let's consider an example dealing with elastic forces. So we have the diagram shown here, and we want to use the data given in the diagram, first of all, to be able to calculate the spring constant of that spring. So, spring constant, lowercase k, change in force over change in position. Remember, we originally defined this related to a graph of force versus distance stretched, and this was the slope of that line. We don't have a graph here, but we do have our diagram to be able to get that data from. So over here on the diagram, we've got a 200-gram mass hanging and a meter sig next to it, and then a 500-gram mass hanging and a meter sig next to it. Well, from the masses of 200 grams and 500 grams, we can get the change in force. Remember, the force is mass times gravity, and convert that mass into kilograms. So then the change in mass, 500 grams, are 0.5 kilograms times 9.8 gravity minus 0.2 kilograms times 9.8. And I'm running myself out of room here with the diagrams. And now we need the distance stretched. What I'm going to do is I'm going to pull my diagram down here, and I'm going to use the edge here as a straight edge. You can pick any point, like the bottom of the spring or the bottom of the coil there on the end of the spring. You don't want to use parts of the mass because the two different masses change. So I'm going to line it up the best I can with the bottom of that coil, right about there. And then I'm going to read this distance off here. It's looking like 71.12, just about even on 71.3 centimeters. So that's going to go with a 0.2, so 71.30 centimeters. And now I'm going to go to the corresponding place on the spring over here. And let's see, we're at 79.5678. It's like 79.88 centimeters. So if we calculate this spring constant, subtracting our forces on the top, that's going to give us 2.94 newtons. Subtracting the values on the bottom, that is our 79.88 minus the 71.3, it gives us an 8.58. So then when we divide that, we get a spring force value of about 0.34 newtons per centimeter. Sometimes we'll need that in newtons per meter. So if I convert it, that gives me about 34.1 newtons per meter. Now, part B. Part B, if the spring has an unstretched length of 17 centimeters, calculate the total length of the spring when a force of 0.24 newtons is applied. So then here is our spring when it is relaxed. And when it is relaxed, it's 17 centimeters long. Now we apply a force to it. And this force that we're applying is 0.24 newtons. And we want to know what this new length is. Well, the new length is going to at least include the 17 centimeters, but then there is some additional stretch there, and that's what we have to calculate. So then new length is going to be 17 centimeters plus what we calculate. Now, to be able to calculate the distance that 0.24 newtons stretches, we're going to use the same idea of an equation, but we're going to write it out in y equals mx plus b form, what's called Hooke's law. So F equals kx. K we just calculated up here, and x is what we want to calculate. F we know it's 0.24 newtons. So then plugging in 0.24 newtons is equal to, I'm going to use the value in newtons per centimeter since we're in centimeters here, 0.34 newtons per centimeter multiplied by x, and that'll give us how much that force stretches it, and I get a value of about 0.7 centimeters. So then if we add 0.7 centimeters here, our new length is going to be 17.7 centimeters. Now, I want to give you a second logic to be able to think of this. Let me give us a little space here. So I'm just going to slide this diagram off to the side. You can also think of our reasoning here in proportional reasoning. So instead of using F equals kx, you could have just taken a ratio of force to distance stretched. In other words, 2.94 newtons stretches it 8.58 centimeters. We've got 0.24 newtons. How much will it stretch it? And then solve down. This x value will be the same as the x value we calculated over there. So it's just two different logics to follow to get to the same thing. Ponder physics.